The goal of exercise 8 in chapter 2 is to write code that produces figure 2.6. Okay, so let's have a look at figure 2.6. The goal here, or the idea here, is that we have a vector A and a vector B, and we want to project vector B onto vector A such that the projection is orthogonal. So you can see that drawing a straight line from B onto A such that this line intersects A at a right angle, that's what I'm depicting here, and that is the orthogonal projection of B onto A. And what we want to solve for is basically this scalar value here, which I call beta. And so the idea is that beta A, so this scalar value times vector A, is exactly this point here. And then, yeah, if you go through the text, I describe how to define that point, that beta term. It's fairly simple. It's also fairly intuitive. I hope you agree that it's intuitive after reading the text in this chapter. But it's really important. It's important for you to understand this concept of orthogonal projection because that's the basis for a lot of applications of linear algebra, including least squares. So a lot of applications in statistics and data science are based on this very simple concept of projecting a vector or a point onto another vector. So here you see the code implementation of the formula to obtain that value of beta, that scalar beta. Okay, so I create these two vectors A and B. And here, now I'm using the dot product. This is going to seem even more confusing after what I said at the end of the previous video, where I showed that this actually gives an error and you need to transpose it. It turns out that is really only necessary for vectors that have an orientation. So basically, this first vector needs to be a row vector. This needs to be a column vector if they both have orientations. If they don't have orientations, then you don't need to worry about that. It is yet another confusing aspect of the function numpy ... If you are annoyed about how confusing and weird and nonsensical that function is, then I'm with you, man. But I didn't write this function. I just teach about it. Anyway, so the formula to obtain the scalar beta is the dot product between A and B, scaled by or divided by or normalized by the dot product of A with itself. And again, this, if you're not following with the text, then this seems to be weird and come out of nowhere. But I promise it's very sensible. I explain it in the text. Okay, so this gives us beta. And then what we need is the projection vector, which is the line that goes from vector B to vector beta A. And then here I'm just implementing all the plotting stuff. Sometimes I use arrows. So I use arrows for the vectors. This I explained in, I think it was the first exercise in this chapter. But basically, the way you use dot arrow, this function is to specify the start coordinates and the length along direction X and the length along direction Y. Okay, so then we can plot this, and this is how the figure looks in the book. In general, when I give you an exercise that says, write code to reproduce this figure, I don't care about reproducing it exactly, and neither should you. You can use colors if you want. You can use different fonts. You can have the arrows, differently sized. None of that stuff matters. What's important is these two lines of code. This is the conceptual linear algebra stuff that is important for you to get correctly. Everything else is just a matter of personal preference.